Swayam Prabha. Digital India. Educated India.
The term pH, pH of a solution, is a measure of the free hydrogen ion concentration in that solution. Free hydrogen ions are nothing but protons. Therefore, the pH of a solution is a measure of the proton concentration in that solution. Plasma pH has to be tightly maintained around 7.4, and that is the issue being considered currently. To understand pH per se, we will look at some basic chemical concepts and the water equilibrium per se. Water is a pH of 7, pH being the negative logarithm of the proton concentration in a solution. To get a pH of 7 for water, the free hydrogen ion concentration has to be 10 to the minus 7 molar. Now, when I say capital M, what is meant is moles per liter. It is referred to as molar, and the term means moles per liter. Millimolar means millimoles per liter. This is nanomolar. For a pH of 7, the hydrogen ion concentration in solution has to be 100 nanomoles per liter. Water has a pH of 7 and the corresponding free hydrogen ion concentration is 100 nanomolar. We just saw that. Plasma has a pH of 7.4 and the free hydrogen ion concentration is 40 nanomoles per liter. Now, let us look at water equilibrium yet again. These are stable water molecules, let us say H2O molecules, and let us see how many stable water molecules there are in a liter of water and how many of those are ionized. A liter of water will have 55.56 moles of water molecules. How did we get that? A liter of water weighs that much, and that is the molecular weight of water. Therefore, 1 liter of water will have 1000 by 18, 55.56 moles of water. And each mole will have the Avogadro's number of molecules in it. Therefore, these many moles will have 55.56 into the Avogadro's number of water molecules. Of that, only 100 nanomoles of water molecules are ionized, whereas most of them remain in the stable state. We will now see what proportion of the stable water molecules is made up of the ionized water molecules. So, those are the stable water molecules, let us say, and a very small amount, 100 nanomoles of water molecules are in the ionized state, giving you 100 nanomoles of free hydrogen ions, which is what keeps the pH of water at 7, and an equal amount of free hydroxyl ions. So, the fraction of the ionized molecules would be 100 nanomoles over 55.56 moles, and that gives us a little less than 2 ionized water molecules for every billion stable water molecules. A minuscule number of water molecules exists in the ionized state, giving a minuscule concentration of free hydrogen ions in solution. However, these 2 molecules or less than 2 molecules of free hydrogen ions for every billion stable water molecules has to remain there, and if it moves a little this way or that way, if it decreases a little or increases a little, it can negate life. And therefore, pH of plasma or the fluids in which cells live in has to be maintained around 7.4, very tightly around 7.4. Some sources will tell you that the free hydrogen ions in solution do not exist as free hydrogen ion, but they would exist as a hydronium ion in combination with a stable water molecule. That is a level of detail. For our considerations, we will consider free hydrogen ions as free hydrogen ions. So, we have this at equilibrium. So many moles of stable water molecules in equilibrium with 100 nanomoles each of hydrogen and hydroxyl ions. Addition of acid, which will yield more free hydrogen ions, or addition of an alkali, which will yield more hydroxyl ions to a liter of water, will disturb the water equilibrium. At equilibrium, or when you have a liter of water, the rule of chemistry is that the product of the concentrations of hydrogen ions and hydroxyl ions will have to be 10 to the power minus 14 molar. This is called the ionization product constant for water and has to be that value. When you add excess acid or extra hydrogen ions, then the other species, hydroxyl ions, will have to adjust itself, or it will have to reduce so as to maintain the product of concentrations of these two species at 10 to the power minus 14. If you add extra hydroxyl ions to the solution, then the hydrogen ion concentration will come down, and that is how the pH becomes more than 7 when you add alkali to a solution. We will see this visually. Let us say these boxes represent stable water molecules and these the ionized water molecules. If we add extra protons to the solution by adding some acid, let us say the concentration of protons added is 10 to the power minus 6 molar. Then originally in water we had 10 to the power minus 7 or 100 nanomolar hydrogen ions and hydroxyl ions. When we have added extra hydrogen ions, now it is at 1 micromole per liter, some of the ionized water molecules will move into the stable state. They will combine and move into the stable state, and you will have a situation where because of the presence of extra hydrogen ions, the hydroxyl ion concentration has reduced such that the product of concentrations of these two species remains at 10 to the power minus 14 molar. Similarly, when you add extra hydroxyl ions to the system, again some of the water molecules in the ionized state will move into the stable state, and you will have the concentrations of hydrogen ions and hydroxyl ions in such a manner to maintain the ionization product constant of water. Excuse me for repetition, we will see this again. Say we have added hydrochloric acid to a liter of water, it ionizes to give protons and chloride ions. Since the hydrogen ion concentration of water has gone up, some of the ionized water molecules will move to the stable state, and the new concentrations of protons and hydroxyl ions will be like that, such that the product remains 10 to the power minus 14. And if you add an alkali to the solution, it would ionize. Let us say you have added sodium hydroxide, it ionizes to give you sodium and hydroxyl ions. Hydroxyl ion concentration has gone up, and therefore some of the ionized water molecules will move into the stable state. The hydrogen ion concentration is reduced from 10 to the power minus 7 molar in water per se to 10 to the power minus 8 molar after addition of sodium hydroxide. The pH now is 8. Now we will see how the presence of carbon dioxide in water will affect its pH. In the last session we saw that metabolic processes in the cells constantly add a net excess of acids into blood, and the predominant acid is carbon dioxide. Therefore, we will consider how presence of carbon dioxide in solution can change the pH of that solution. Let us take 1.2 millimolar carbon dioxide. Why did we want that number? Because that is the concentration of carbon dioxide in arterial blood. If we add 1.2 millimoles per liter carbon dioxide to water, what would be the pH? How will we add 1.2 millimoles per liter carbon dioxide to water? The easiest would be to let water stand in an environment of 5% carbon dioxide, or you can bubble 5% carbon dioxide through water. Atmospheric air normally has nearly zero carbon dioxide concentration. So, when I say 5% carbon dioxide, it is a mixture of 5% carbon dioxide and 95% air, or another popular mixture available commercially is 5% carbon dioxide and 95% oxygen. One of these two mixtures you can use. 5% carbon dioxide gas mixture is used in the cell culture laboratory to incubate cells, to give cells the environment in which they normally reside in the body. And when you leave water in an atmosphere of 5% carbon dioxide, you would get a concentration of 1.2 millimoles per liter. We will see why. Now, at 5% carbon dioxide, the partial pressure of carbon dioxide in that mixture would be 5% of atmospheric pressure, and that would be roughly 38 millimeters mercury. Let us round it off to 40 millimeters mercury. For every millimeter mercury carbon dioxide, the dissolved carbon dioxide in water which is kept in that environment would be 0.03 moles per liter. Therefore, when the partial pressure of carbon dioxide is 40 millimeters of mercury in that environment, the dissolved carbon dioxide would be that into 0.03, which is 1.2 millimoles per liter. Sajal was a postgraduate student with us 2 years ago, and he did this experiment. He used a carbon dioxide incubator which is used for cell cultures. It has a 5% carbon dioxide. He left some water in the incubator and allowed carbon dioxide in that environment to equilibrate with water, to dissolve in water. Sajal was being a little too careful. He in fact let the water stand there for 48 hours. Carbon dioxide would have reacted with some of the water molecules and yielded carbonic acid, which would have given some free protons and bicarbonate ions. So, there will be some dissolved carbon dioxide remaining as carbon dioxide, but some of it would have ionized to form free hydrogen ions. Therefore, the pH of water should have dropped because new hydrogen ions have come into solution now, and that will cause some of the ionized water molecules to move into the stable state. You will have a situation where you have more free hydrogen ions and less hydroxyl ions. So, what would be the new pH of the solution? Sajal took that beaker of water out and checked its pH. The new pH was 5. So, if water had 1.2 millimoles per liter carbon dioxide in it, pH of water would be 5. What about plasma? If you take a sample of arterial blood, the carbon dioxide concentration in that will be 1.2 millimoles per liter, and we know that pH of blood is 7.4, though we have so much carbon dioxide present in blood. So, the question we have now is why plasma pH 7.4 even though there is 1.2 millimoles per liter carbon dioxide in it. We know that pH of water with that amount of carbon dioxide is 5, but what makes the plasma pH to be at 7.4? If this reaction had occurred in plasma, then there will be an excess of free hydrogen ions and pH should have dropped. Why is it that plasma pH has not decreased? In fact, it is increased to more than that of water. The answer to this question is that plasma pH is at 7.4 because plasma has an excess of bicarbonate ions. 24 millimoles per liter bicarbonate ions. Because one of the products of this reaction is an excess, that reaction cannot proceed rightwards, and that is what prevents ionization of carbonic acid to form more free hydrogen ions. This excess of bicarbonate in plasma actually comes from kidneys. We will see that later. And it is that excess which prevents carbon dioxide from forming new protons. Some of you might have that question. If an excess of bicarbonate is present, new protons may not be formed, but what happened to the protons that are there in water already? Why is pH not 7 but 7.4? The answer to this is that bicarbonate can ionize to form hydroxyl ions. And if hydroxyl ion concentration increases, we have seen already that hydrogen ion concentration has to decrease so as to maintain ionization product constant of water. It is because of this reaction that plasma pH is more than that of water, or the free hydrogen ion concentration of plasma is 40 nanomoles per liter, while that of water is actually 100 nanomoles per liter. My references for this reaction are these. While we understand that even though 1.2 millimoles per liter carbon dioxide is present in plasma, plasma pH is not less than 7 because it has an excess of bicarbonate ions. Plasma pH is in fact more than 7, it is 7.4. One question that might arise in some of your minds now is that why do we need to have any carbon dioxide at all in arterial blood? Why can't the lungs remove all the carbon dioxide in venous blood and send the blood into arteries free of carbon dioxide? Why have so much carbon dioxide at all? And then why make so much bicarbonate? Why should the kidneys put out so much bicarbonate? In order to prevent acidification of plasma due to that carbon dioxide. It is a useful concept here that carbon dioxide is not the pH offender in this case. It is in fact bicarbonate. That amount of bicarbonate has to be there in plasma for some other reason. We will see that later. The kidneys have to provide that amount of bicarbonate, and we have already seen that bicarbonate ions can form hydroxyl ions and therefore increase the pH of plasma. Therefore, to prevent alkalinization of plasma because of addition of bicarbonate ions, the lungs release a certain amount of carbon dioxide into arterial blood. Therefore, arterial carbon dioxide is necessary to balance the excess bicarbonate ions. Of course, then the question is, why so much bicarbonate in blood? Why do the kidneys have to put in so much bicarbonate into blood? We will reserve that question for later. So, we now have a situation where the equilibrium status is 1.2 millimoles per liter carbon dioxide at equilibrium with 24 millimoles per liter bicarbonate, and the pH is 7.4 in that condition. Is there a general rule relating carbon dioxide concentration, bicarbonate concentration and the resulting pH? The rule is pH is pK plus log concentration of base over concentration of acid. This is the Henderson-Hasselbalch equation. So, for the bicarbonate carbon dioxide buffer pair, as they are called, we will see why they are called the buffer pair later. pH would be pK plus log concentration of bicarbonate over concentration of carbon dioxide. Now, what is pK? If we want to understand pK, a useful technique would be to make this term 0. We can make this term 0 if we have same concentrations of bicarbonate and carbon dioxide. You could keep it at 1.2 each or 5 each or 10 each, whatever. If you have equimolar concentrations of acid and base, then this would be log 1 and that would be 0. This term would reduce to 0, and now pH of the solution would be the pK. pK is therefore the pH of a solution when you have equimolar concentrations of acid and base. That is experimentally determined. You add equimolar concentrations of acid and base to a solution and you test what the resulting pH is. That is indeed the pK of that solution. For the bicarbonate carbon dioxide buffer pair, pK is 6.1. The calculations would go like this. pH of this system would be the pK plus log 24 by 1.2, which would be log 20, and that would reduce to 7.4. That is how we get plasma pH. Then we can back calculate and say that this is going to give us a free hydrogen ion concentration of 40 nanomoles per liter. Well, pH of arterial blood is 7.4, and that comes about because the ratio of bicarbonate to carbon dioxide in arterial blood is 20. 24 by 1.2 is 20. Now, when blood courses through tissues, carbon dioxide is added to venous blood, and the next consideration will be, will the pH of venous blood change when new carbon dioxide is added to plasma? We will consider that in the next session. Thank you for watching.